Hello, time check. This is 11:49, still in the morning. So good morning, family and friends. I welcome you all to today's learning. We're going to look at a new topic that I've chosen, which is waves. General properties of the waves. The waves. Now, the guy presenting, oh, by the way, this is coming from physics, and the guy present, this is coming from physics, and I'll make it as quick as possible so it just lasts for 60 minutes. And the guy presenting, the name of the tutor is that. His phone number is +26 097 5578 694. That is his WhatsApp number. You have a question, you can just send him a question on that number, and he will definitely attend to your question. So let's get the part started. Having introduced myself, my name, the expected or the approximated duration of the presentation, the topic, as well as the subject where it's coming from. So let's get started. So we'll be looking at waves. Waves is not really a long topic as in per se. It's just something manageable. So to start with, allow me to give the definition of the word wave. But you see, many scholars have defined that word in many ways. Many scholars have defined the word waves, in many different ways. I think this is the one that I thought would help us to understand what happens when and where. So we are saying the wave can be described as the disturbance that travels. Yeah, so meaning for the waves to be produced, there must be the disturbance on the media. The waves cannot be produced when there's no disturbance. So we are saying for the waves to be produced, there must be the disturbance on the media, and then that disturbance is able to travel from one point up to the other as it carries energy. I should have included there, as it carries energy. That's how best I can describe it. Of course, when you check from different books, different scholars have described waves in many ways. Yeah, but that was my own way. So I'm saying that the disturbance that it travels through the media from one point to the other. Yeah, so there must be a media where all these waves are traveling as they move from point A up to point B while carrying energy. Now, you see, the media can be described in many ways. The media can be described in many ways, which we are going to look at later. But for now, allow me to just give you insights or examples, general examples of waves. Before even come to categorize them, let's just look at the general waves. And then having looked at the types, that's when we're going to now classify them based on the categories that will come up with later. So we have the water waves. So in here, the media is the water. When there's a disturbance on the water, you see that the wave will travel. The other one is sound. Sound. sound waves. The other one is light waves. Light waves is another example of waves that we can talk about. We have light waves, though this is not supposed to be here as a standalone, because this one is included in the electromagnetic waves. Electromagnetic waves, we have a lot of them that are falling in here. Yeah, so they allow me to remove the light wave, because the light wave is falling in the electromagnetic waves. So in the electromagnetic waves, there are quite a lot that we're going to look at later. Then the other one is the wave on the rope. When you have a rope, one end tied at a fixed point, and then you start pulling the other end up and down, find that the waves will be produced. So that is another example of a wave. Yeah, these are the ones. Now we are saying basically, in regardless of these ones, that these examples that we've looked at, these waves can be categorized in two ways. These waves can be categorized in two forms. One is what we call a transverse wave. There's what we call a transverse wave, as well as the longitudinal wave. Yeah, but for today, we're never going to talk about the longitudinal. I just wanted to pick one. We're never going to look at the longitudinal today. We'll just look at a transverse wave. This will be a subject of another day. Yeah, so we're saying there are two types of waves, and these are transverse waves as well as longitudinal waves. Now, when you say there are differences and the similarities that fall within these types of waves, now, what are the aspects that we have to look at? What are the things that we need to consider? Remember, when they say give two differences between an animal, and I'm speaking as an examiner, when they say give two differences between an animal, and a human being, when you're giving the differences, you have to specify the aspects. If you say the way the animals, or if you say the way the human beings live, the way of living, talk about that as a single aspect. How do human beings live in comparison to the animals? If you talk about the way they walk, how do animals walk? Let me say a dog. How does a dog walk compared to the human being? You pick an aspect at a go. So the first aspect here that we can look at, if you are told to give the differences between a transverse wave and a longitudinal wave, you have to first look at the movement of the vibration, the movement of the vibrating particles. These particles, when they're vibrating, how do they move? In the transverse waves, how is the vibration of the particles? In longitudinal waves, how is the vibration of the particles? That's the first aspect that you can look at when you are told to distinguish them. The other one that we can look at, when you're told to distinguish, you can look at the examples of waves. Yeah. I can also look at that. So these are two aspects that you can consider when you're told to distinguish the waves. Transverse wave as well as longitudinal waves. Okay, we go to the next page. So having done so, now let us look at the transverse wave. Remember what I said? Just pick on one specific type of a wave. We talk about it at length, and then we conclude. So the one that we're going to talk about today and now is the transverse wave. Now, when you say a transverse wave, how do you define it, in as much as you want to separate it from the other type of a wave? Now you see the let me do this. The transverse wave, we are talking about transverse wave here. Oh, okay. Let me do this. Oh my goodness. Okay, it doesn't really matter. I'll do this. Good. And then I click on it. Good. So in as much as we're looking at the transverse wave, what are the things that we need to know about it? Yeah, what are the things that we need to know about the transverse wave? So I say This is a type of a wave. I'll be underlining the points that are very, very much cardinal in the definition of the transverse wave. I'm saying this is a type of a wave where the vibration of the particles are at the right angle, or they are perpendicular to the direction of the wave. Remember, when you're defining, I said the first thing that we have to look at is the vibration of the particles. That is one way in which we can distinguish the definition of the transverse wave as well as the definition of the other type of the wave. So I say if the wave is going in that way, perpendicular, we're talking about 90 degrees. So the vibration of the particles must be perpendicular. Must be perpendicular. Now, I think this one was not even fully described because not only at 90 degrees, it must be up and down. So that kind of vibration is what is expected. The particles have to vibrate in an up and down way, perpendicular to the direction of the wave. We have the wave going this way, and then the vibration of these particles are at 90 degrees. First aspect when you want to distinguish the transverse wave from the longitudinal wave. Now, they like asking such questions. They like asking such questions. How do you show the vibration of the particles in a transverse wave? So I drew it somewhere here. I had it put here so that we can understand what this means. This is talking about the vibration of the particles as the wave is going either that way or that way. But the truth of the matter is that the vibration has to be at 90 degrees, right angle, or perpendicular. So in your definition, you make sure that the perpendicularity has to come out in your definition when you're talking about the transverse wave. Now, among those waves that we had on top, among them were not even mentioned. Some of them were not even mentioned. So now these are the examples of transverse waves. Remember, I said when you want to give the differences between a longitudinal and a transverse wave, it's so important that you talk about these aspects that are on top. Now, in case the question asked you to give the examples of the transverse waves, whose particles vibrating on the media to produce a wave is done at a right angle. Which ones are they? One, we have the water wave, and I'm going to explain how this happens in the best way. The first one is the water wave. What is the second one? The wave on the rope. The third one, the electromagnetic waves. Now you see here there's waves. That's why there was an S that was meant there. Electromagnetic waves, because there are a lot of waves that are falling in the electromagnetic spectrum. In the electromagnetic spectrum, there are a lot of components that are there. Among them, some of them are waves. So we've got light waves, which is positioned at number 4, visible light, and then we've got the radio waves. We have got the microwave, which is the TV waves. We also have the X-ray. Those are rays anyway. The micro, yeah. Those other ones are rays. Yeah. So for now, just stick to this. The light wave, the radio wave, as well as the electromagnetic waves. These are the waves that are found in the electromagnetic spectrum. So you can, if you don't want to restrict yourself, do not just say electromagnetic waves. You are restricting yourself. If they ask for more, split the electromagnetic waves into these various components, 3 of them. So these are examples of the waves, as well as the vibrational movement of the particles as a wave travels from one point to the other. Now, if you can allow me to explain a little bit, how does this happen? Or how does, before I even go to that, how does these waves qualify to have the particles vibrating perpendicular to the movement? Suppose, let me just talk about one. If this is water, this water, this is the level of the water in the river and the lake, the ocean, and any water body. Now, when you have a stone dropping on the water, or some of us that have been to the rivers, let's say there was a crocodile by the bank of the river. Now, as we are approaching the position where the crocodile is, it jumps on top of the water. You find that this crocodile will drop on the water, forcing the water that is here to tumbui, you know what I mean? As a result, you are gonna find water moving like that. Where the particle which is here, it will get on top, and then it will also get at the bottom. The truth of the matter is that is a distance it is covering vertically from that point to that point, as the particle is going that way. So there is an up, there is a down and upward way. Because for the particle to move from here to get to that, it has to go a little bit down. Now, again, as it moves from here going to that point, there is a certain height which is attained in an upward way, perpendicular. What about waves on the rope? What about waves on the rope? How can you say? Supposedly, you have this rope tied at a tree. Then you have this person who pulls the rope up and then pushes it down. As a result, we're going to have such kind of things generated. Now, with the rope, how is the vibration of the particles best explained? Now, supposedly, you had put a ring here. You had put a ring here, very close to the end. Then you start moving the rope in this arrangement. You find that this ring will be at some point here, 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 until to be finally at the end here. All in all, there's a certain height, there's a height attainment in one way or the other. And this also happens to these electromagnetic waves. We'll come and look at them when we start looking at the electromagnetic spectrum itself that falls within the waves. So these are examples of transverse waves. We go to now features, the diagram, the one that I explained, and then the features also that are present on the electromagnetic waves, on the transverse wave rather. So supposedly this is the initial point where you had the rope held from, and this is the point, the other point where you had your rope tied on the tree. Now, remember I said if you have a ring here, maybe I'm using a different color. If you have a ring here, then you keep moving the rope up and down. See what happens at some point, there's gonna be a maximum point, the maximum height that, okay, let me just say, there's gonna be a point when the ring will get to that point. So the maximum point of a ring, the maximum point of a wave, which is the same as that point here, which is the same as that point there. The maximum point of a wave is what you're calling a crest. So the crest is just the maximum point that the wave attains. Now, in as much as you do that, at some point when the wave is here, when the ring is here, to at some point be forced to get to the lower part of the wave. The ring will be at some point here, at some point here, and at some point there. So that is what we call the trough. The trough is the lowest point of the wave. Now, not on that, there are quite a lot of features. Now, there is a distance. Remember, this is the media which is not disturbed. That's why they use the word equilibrium. You see, the part is in equilibrium. This part is not disturbed. This part of the wave, this part of the media is not disturbed. Now, from here up to the highest point of the wave, from here up to that point. Okay, let me just remove this thing here. Okay, what color can I use? Red. Okay. Now what we're saying is that from here, from the undisturbed area up to that point, up to the maximum there, the maximum point, this is what we call the maximum displacement. So from the undisturbed area up to the maximum, up to that point there, which is what we call the maximum displacement of a wave. This is the maximum displacement of a wave, which we can call by the word amplitude. So the amplitude is the distance between the undisturbed area up to the highest position that the wave attains. Now, there was a question that came in I think 2020, the last year's paper. There was a diagram of that nature. Okay, now see what they did. They drew the diagram like they had drawn a line from here up to that. And then they said this distance is 8. Then they asked the learner to identify the size of the amplitude. Never be deceived by this. All you need to know is that the amplitude is from here up to that. Now, we also, if this is the maximum displacement, there also must be a minimum. Now, a minimum displacement of a wave is this one, which is here. So the minimum displacement of a wave is what we call the trough. Maximum amplitude, minimum trough. Not trash, trough. So this trough here is the opposite of the amplitude. Amplitude, maximum, trough, minimum. Now, one thing that you need to know is that the amplitude is equal to the for a regular wave. The amplitude is equal to the what do I mean? What I mean is that the amplitude is equal to a distance. Let me just say 0.5 is 0.5, the distance between the trough and the crest. I hope this makes sense. I don't know. To me, it has to make sense to you either. So what I mean is that maybe let me just put in the single line. What I mean is that the amplitude is halfway the distance between the distance between the trough and the crest. What does that mean? It just means what I have just explained from a last year's paper. Here, that's where I've got a trough, and here that's where we have got the amplitude. Now, the distance between the amplitude and the distance between the crest, not the amplitude, the distance between the crest here and the trough was 8, was given to be 8. Therefore, following this statement that I've written here, the amplitude is supposed to be halfway the distance, which is going to be 4. Now, both the trough and the crest are very, very, very important in the determination of the amplitude. And do not be deceived, because we're talking about the maximum displacement. Now remember, displacement and distance, they are talking about the length or the increase in the path. Yeah, so it is measured in meters. Displacement is how do I explain it? The displacement is the increase in the length between 2 points, but it must be in a specific direction. So it has to be measured in meters. Okay, one more thing. There are some points that are very, very, very much identical. There are some points that are very, very much identical. Points such as crests. So we have a crest here, we have a crest here, and we have a crest here. If you are to count, we have 1 here, we have 2 here, we have 3. These points are identical. So the distance between 2 identical points on a wave is what we call lambda wavelength. This one, which is here. So this one here, we are saying that the wavelength here, the wavelength is the minimum distance between two identical points. So if the points you're talking about are only the crest, then we have to consider the consecutive crests. Yeah, we have to pick two crests. Let me just have a diagram from this page to avoid going back. So if you have this as your wave, the distance between this crest and that crest gives us the wavelength, which is the symbol is a Latin word lambda, Greek letter lambda rather. So the lambda is talking about this lambda here. The lambda is the minimum distance between two identical points. For the amplitude, they will use the word displacement. Here they have used the word distance. So remember the similarities between displacement and distance is that they are both measured in meters. Displacement and the distance are both measured in meters. So that means both the amplitude as well as the wavelength are measured in meters. Except that the symbols are different. Here we use the symbol A, and here the symbol used is this Greek letter, which is lambda. Now, we can go to the next page. Let me just slide it a little bit down. Oh, okay, here. Now, there's quite a lot again that we need to know here. Before we go to that, let's talk about the frequency. Forget about this for now. So supposedly we have a wave. And this is our wave. Wave ya tu ili hapa. Na hivi wave ya tu ni bend, that's very bended. Okay, that is our wave. And then it goes that way. Understanding very well that from here up to that, we have a lambda. We have our lambda here. And then this height here is our amplitude. Now remember, the amplitude must be capital A. When you use small a, you're talking about acceleration. So this is our amplitude, this is our trough, this is our crest, yeah? Now, there are times when you have a watch, say for instance, we have this thing as our rope tied here, that is being pulled up and then down like that. Now, when you are very, 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 very fast, when you are very, 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 very fast, alongside with you, you have a watch. You can count the number of waves that are being produced in a second. When you are very, very fast in playing around with this end of the rope. So when you are very, 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 very fast playing with the end of the rope alongside with you, you have a stopwatch, you can count the number of waves that are produced in a second. So the number of the number of waves that are produced in a second, that's what we call frequency. So this frequency here is talking about the number of complete waves that are produced per second. So in other words, it means the number of waves that are passing through a point. It's just one and the same. Now, we are saying the number does not have units, it's just a number. The number per second. Number per second. Now, this frequency, it must be small f. These are things that make people fail physics because they pay attention very much to chemistry. How do they pay attention to chemistry? When you're talking about the periodic table, they are so particular. Carbon, they will just write C. Chromium, they will just write R. Copper, they will just write Cu. Manganese, they will just write Mn. A tin, they'll just write W, 1 gate. Sodium, they just write Na. They are so particular with the elements and their symbols, but they pay less attention to physics. Physics is also science. Yeah, so the frequency must be denoted by small f. Just look at this one here. The moment you use capital F, you're not talking about frequency, but you're talking about force. Just like I said, amplitude, you use capital A. The moment you use small a, you're talking about acceleration. Yeah. Any, when you use capital N, you're talking about newtons. When you use small n, that is the number of waves. Remember, even we said period in the pendulum, period is equal to is a period is a time taken t over n. So the moment you put capital N here, you are getting yourself in an awkward situation, talking about newtons. So these are things that you need to know in as much as we approach physics. Some say physics is easy because it just involves the numbers, and me, I'm good at mathematics, I'm good at numbers, but they pay less attention to these cardinal things. And then, having talked about this, we can even talk more about T, and that T. This T is meant for time. This T is meant for period. So again, here, you must be very particular in as much as you claim that physics is years. Okay. So we have talked about this. So this part here, we are saying the units are Hayes as well as second minus 1. So second, remember from the indices, second minus 1 is the same as 1 over seconds. That is the frequency. The frequency is a number of waves that are produced in a second. So when you are very fast in doing that with your rope, you end up having a lot of waves that are being produced in a second. Now, whether you are very fast or you are very slow, whether you are very fast or you are very slow, the amount of time is gonna take. Here we're talking about the number of waves produced in a second. Now, the time it's gonna take, whether you're very fast, you're very slow, the time it's gonna take to make one wave. Whether you're very fast or you're very slow, the time it's gonna take to make one wave, that's what we call period. So period is a time taken to make one complete wave. Do not mix the two. Number of waves produced. Number of waves. Here, the time taken to produce the wave. So in a situation where, let's say, before I go to that, so period is a time taken to produce a wave, and then the units, because it's time, remember it's in seconds, not hours, not days, not years, not centuries, not millennium, seconds. Pay attention to these small things. Then the symbol that we use here is capital T. The moment you use small t, my dear, you are talking about the amount of time recorded, not the period. Now, let's take this practical example. If the time it takes is 20 seconds, and the number of waves that we make is 10. It's just a number, doesn't have units anyway. If the number of waves made is 10, and the time it took is 20 seconds, how can we derive a formula that is going to help us to find the number of waves that were produced in a second? Or how can we come up with a formula that is going to help us to find the time it took to make one? Here there are 10, and it took that time. So what formula are we going to use? We can say period D is equal to, remember, as we are dealing with to complete one wave, the time taken to make one wave. So we're gonna divide, use the formula, we're gonna write the time it took divided by the number of waves. That will give us 20 seconds divided by 10. It means one wave, it was taking 2 seconds. To make one wave, it was taking 2 seconds. And to make 10, it took 20 seconds. See how easy it is? And if we are to find the frequency, the number of waves that were being produced in a second, what do? Frequency is equal to 1 over t. Now remember, when you use the sign over, it means we are dividing, yeah? Which you can say 1 over, now what is our t? Look at our t here, which is t, again divided by n. It's not making any sense. So the moment you have that, just take the n on top and then the t gets to the bottom. And the frequency is n over t. Why n over t? Remember, this n does not have the units. The only units that you're going to have, the n does not have the units. The only units you're going to have are those for time. And remember, it's a numerator. That's why we're coming up with the per second, because we are dividing with the time, which is in seconds. So with all that said, I'm sure I can even go to the next page, which is talking about these formulae that are very, very, very important. So some useful formulae. The useful formulae that I've put out are just 2, but there are quite some more. But for now, let's just stick to this, because that is the content of our science. I wanted to get something, but I'm getting something there. Okay, this is not hard. Yeah. Some useful formulae. It's just the same thing that I've just explained, except that this one limits our thinking. Limits our thinking. So if you don't want to go by that, you can just say frequency is n over t. It's just one and the same. Now, once you have the frequency, and we know that from a wave we can get the lambda. Once you have the lambda and you have the frequency, okay, let me bring you to this. Come to think of this. We have a wave. Not a wave, we have 2 waves. Okay, just for now, keep this in mind. We're trying to look at the relationship between frequency and the wavelength. Allow me to come up with this. I want this to be practical. We have 2 waves. The first one here, see how it is? This is wave 1. Then we have wave 2. This wave 2 is quite different from wave 1. This one is bigger. Let's say the lambda here is 20. And the lambda here is 7. Okay? Okay? Good. Then, which one do you think, which one do you think is likely to, remember the frequency? The number of waves produced per second. Come to think of this wave here. Let me use a different color. Come to think of this wave here, and that wave there. Do you think they're going to have the same number of waves that will be produced in a second? Of course not. Why? Because of the frequency in wave 1 is small, the frequency in wave 2 is big. So the frequencies are different. Therefore, the number of waves are going to produce per second, or the wavelength is different. Therefore, the number of waves are going to produce per second will be different, which also depends on the speed at which, you understand? So out of that, there is a general formula that we use, and this is a general formula. And we're gonna use this general formula even when you start looking at the electromagnetic waves. They ask for the properties that are general for all the components that are electromagnetic waves, and one of which which I'm borrowing from the future, is that they all obey this formula. So this is the formula that we use when you are solving questions. These formulas are very, very, very important. You make sure that they stick at the back of your mind. These two. We are finishing very soon. We are finishing very soon. Okay, so now let us look at, remember when you have questions from the explanation, do not forget to hit the number. The number is +26 097 55 78 694. Do not forget to hit that number. In case I'm so fast you didn't get that part clear, you can still reach me on that number and I'll definitely get back to you. So let us look at the practical examples. So how many do I have? 1, 2, and then thereafter there is an exercise. Oh, okay, review work, there's an exercise. So we only have 2 questions. Just 2 questions, and these are the ones that we have. So pay attention to the question, attention to the question. Make sure the formula are stuck at the back of your mind, because we will not be going back to get the questions, the formula. So exam sample questions, this one is just coming from somewhere, but this one is from a past paper, 2020. And this is not fair anyway. That's how life is, because I'm just going to solve very few questions, just 3. But the exercise has got 1, 2, 3, 4. Anyway, there's nothing unfair about this. We are learning. So let's look at the examples. We are saying a wave travels at 30 meters per second. So do not, okay, do not forget that that is a speed, meters per second. Speed is 30, okay, meters per second. But maybe in the interest of time as well as neatness, allow me to use the pen, the keyboard. So you're saying the speed is 30 meters per second, 30 meters per second. Oh, then allow me maybe to say data so that we understand what we're looking for. So the data, we have number 1, we are given the speed, and okay, let me change the position here. Seems we're gonna get interrupted. Okay, so the data here is 1, we have the speed. The speed is 30 meters per second. Then the other thing here, they're saying waves travels at that speed. It passes through a certain, it moves through a certain media. Now, if 10 waves pass through if 10 waves, that's our speed. Now they're saying if 10 waves pass through a point per second, you know what that means. The number of waves produced per second, that is frequency. So the frequency that we have is 10 per second hertz. Per second hertz. So what are we going to do? What are we going to do? Remember, we have 10 second taken. Sorry about that. So we have 10 second, and then to the power minus 1. To the power minus 1. So that is the frequency, and that is the speed. Then the question, simple as it may be, the question says, what is the frequency? The frequency is already there. The number of waves that pass through a point, that is the frequency. So without even wasting much of the time here, just know that the frequency is 10 second minus 1. That is the frequency. The information is there. Then B, find the wavelength. Remember, speed is equal to lambda times frequency. So we are looking for the wavelength, lambda. What do? We divide by frequency, So that goes, and our lambda is gonna be, the speed is 30 meters per second, 30 meters per second minus 1 over the frequency is 10 second minus 1. Now, what can you see from here? What we can see is that second minus 1 and second minus 1 will cancel. That is the beauty of doing the right substitution. That is the right thing. That's the beauty of doing the right substitution. So what just remains is 30 meters divided by 10, and our lambda is gonna be 3 meters. Because the moment second minus 1 cancel, the 0 and the 0 will cancel, and our answer just remains 3. So that is how you play around these sample questions. Then we have question number 2. Here, question number 2, there isn't much to admire. It's very simple. Now let us look at what we have. Question number 2. It says the following diagram shows a water wave. Even if they did not specify that this is a water wave, but something that we know is that it's a transverse wave. Maybe if I wanted to make it longer, I could have said A, what type of a wave is shown above, then 2, or exactly the same question that I was talking about, having the 8. I thought I'd known. I just saw it from somewhere. So one thing that we know, this is the undisturbed area. With this as our trough and this as our crest. And remember what I said from the top, that the amplitude is equal to half of the distance between the trough and the crest. If you can remember very well, this is what I'd said. That the wavelength is halfway the distance between the trough and the crest. And the distance halfway which they have given us is this 8. So to find the amplitude, the only thing we're gonna do is to divide 8 by 2. So it's gonna give us 4 meters. Oh, now these are in centimeters, so we're just gonna indicate the way they are, because that's what we are given even here. But if there was need, if this is paper 2, if this section B they asked to solve, definitely we're supposed to do those conversions. So the amplitude is 4, either of the 2. What is going to determine now is the wavelength. The wavelength is the distance between 2 identical points. Now you see, from this point here, we are getting down. That point, we have just gone up. So the identical point will be when we do that, because again, starting from here, getting down is as good as starting from here. So these 2 are identical points. So if the distance here is 5, and this is a regular wave, and the distance here is 5, so the lambda is supposed to be 10. 5 plus 0, 5.0 plus 5.0, and that gives you 10. So from the amplitude, we have A and B winning, and then from the wavelength, only A wins. So A wins them all. So that is how you can play around the waves. There's nothing hard about waves. So for now, that is the work that was prepared. Then after that, we have the review work. We have a small review work, and this one is also coming from a past paper. this one from somewhere. So the review work says a wave source of frequency 1000 Hz emits waves of wavelength. They have given us the frequency and the wavelength. What is the period? Remember, period, the number of waves produced. T, oh no, sorry, the period is a time taken to produce one wave. Then B, what is the speed? Of course, you know the formula to use. And then question 2, a figure below shows a wave traveling through air. It could be an electromagnetic wave. And then which labeled the distances represent one wavelength and one amplitude of the wave. All that. The work is very easier. So as soon as you are done, I want you to get done with it, send the work to the number 6975578 Now, learning has to be interactive. I'm a kind of person who answers questions each time they come for as long as I'm not sleeping. I'm always online, I'm always on WhatsApp. Whenever the question comes, I'm definitely going to attend to it. That's how interesting learning can be. Okay. I think that's where we end for now. Enjoy the day. Don't forget to mask up. Don't forget to subscribe to my YouTube channel so that each time I post something, you will be notified that someone posted something. Goodbye.